In this lecture, we'll look at relationships between two quantitative variables, and we'll talk about correlation. In this lecture, we're covering displaying and summarizing relationships between two quantitative variables. Recall that for single quantitative variables, we can display the data using a histogram and summarize with the mean and the standard deviation. Remember, those are measures of center and spread, respectively. Here's an example. Here's the data on male students' heights and weights. We see the mean, the standard deviation for each group, or for each variable, one for height, one for weight. And we see displays, histograms, one on the left for height and one on the right for weight. What do these tell us about the relationship between height and weight? The answer is nothing. The reason why is we're looking at paired data. For each student, we have two observations, a height and a weight. By looking at the two variables individually, we take away that relationship. It makes it impossible for us to explore the relationship between the variables. So, if we're interested in a relationship between two quantitative variables, we'll display this relationship with a scatter plot. The explanatory variable, which is the x variable, will go on the horizontal axis, and the response variable will go on the vertical axis. For example, if we're looking at the relationship between height and weight, which should be graphed on the horizontal axis? In other words, which is the explanatory variable? Well, it's the height. It makes more sense to say that weight depends on height than height depends on weight, because as a person grows, as their height changes, their weight tends to change as well. However, if you have an individual person who gains weight or lose weight, they don't also tend to lose height or gain height. Here's a picture. Each of these points represents one individual. The one I've just circled represents one with height 74 inches and weight a little under 240. To generate a scatter plot, we look at each individual and plot an ordered pair. The first term in the ordered pair will be the value for the explanatory variable. The second term in the ordered pair will be the value for the response variable. Let's take a look at using Excel to generate a scatter plot. Here I've taken the SAT scores in math and verbal from the first few respondents to the student survey. I wish to generate a scatter plot with math SAT score as explanatory variable and verbal SAT score as response variable. To do this, I will go to the Insert tab and I'll go over to the charts. There's an option here for recommended charts, but if you notice up here, there's one for a scatter chart. So I'm going to click the button for scatter. I don't want lines connecting these, so I'm going to pick just the plain one in the top left. And notice there's nothing in it. Well, I haven't told it what the data is yet. So I'm going to go up to the top where it says data. Notice I'm in the design tab at this point. Here it says select data. And I would ask for the chart data range. So I'm going to click on the little box over here and I'm going to select math and verbal. I'm going to take them both at the same time. If you notice in the background, the scatter chart or the scatter plot has automatically been filled in. I'll click OK. And now notice if you hover over each point, you'll see that this point is 420, 500. That's the second entry on our list. Notice that Excel has automatically taken the first column to be the explanatory, to go on the x-axis, and the second column to go on the y-axis. There are several things that we can do to change this format, changing the labels, changing the where the lines are drawn as we go from left to right and from top to bottom. We can even select where the origin is, in other words, where the axes intersect. By default, Excel will try to make the origin at 0, 0. That's why all of our data are squeezed in here to the top right. So maybe we want to change that so that the minimum value on each axis is 400. To do that, I'll right-click on the, I've just right-clicked on one of the values down here, and I'll click on Format Axis. Here where it says Bounds, I'll change the minimum to 400. When I press Enter, you can see the plot change in the background. I'll click the X up here in the top to close this out, and now we see our horizontal axis goes from 400 to 700. I'll do the same thing on the right, on the vertical axis. I'll right-click, Format Axis, and I'll change the lower bound again to 400. When I close now, we see that this gives us maybe a better picture of what our data looks like. That's how you create a scatter plot using Excel. Now, let's use the same data to create a scatter plot using our calculators. You can see the same set of data that we used back in the background. I've already entered the math values into L1 and the verbal values into L2, making sure that corresponding entries are next to each other. You should have 14 of them. If you're following along, pause the video and go ahead and punch those numbers into L1 and L2. When you're done, we're ready to set up our plot. The first thing I want to do is set the window. So I'll hit the window button and we'll enter our minimum and maximum values for X and Y. Like we did with Excel, let's make our minimum values for both the X and Y axis 400. We'll make the maximum values 800. Now for the scale, we don't want to count this by ones, so let's maybe count it by 50s. For the Y-min, we'll set to, oh, not positive, 400. Y-min is 400. I accidentally hit the negative key. Y-max will be 800. And we'll count by 50s. You don't need to worry about the other options. Next, we want to make this a statistical plot. So if you look up above your Y equals key, you should see something that looks like stat plot. So I'll punch second and then go into stat plot. And let's edit the first plot, plot 1. So I'll push enter. Now, the cursor is blinking over on, but off is highlighted. So I'll push enter to turn that on. And I'll go down to select the type. You may notice a couple of things here. You see a histogram, you see even a box plot. These are all things that you can create on your calculator. But now I want to focus on scatter plot, which is in the top left. I'll push enter. And then down, my X list is in L1, so I don't need to do anything with that. My Y list is in L2. Next, it has the mark. What do we want each point to look like? By default, it's a square. We can also make it a little plus, or just a dot. I recommend using either the little square or the little plus. I'm going to leave this one at the little square. So now we're ready to see our graph. To do that, push the button that says Graph. It's in the top right of your keyboard. And there you see our scatter plot. Once we have a scatter plot, we'll say that the two variables have a linear relationship if the points on the scatter plot all seem to be clustered around some straight line. We'll say the relationship is positive if the points slope upward in general from left to right, and it's negative if the points slope downward from left to right. Let's look at an example of this relationship. Here again we see a scatter plot displaying this relationship between male students' heights and weights. What are the form and direction of the relationship? Well, the points seem to be more or less clustered around the blue arrow, which looks like a line. So we'd say that this relationship has a linear form. The line goes up as we move from left to right. You might say that it has a positive slope. So the direction of the relationship is positive. Whenever we have two quantitative variables that share a positive linear relationship, that means that we'll see more points to the left of center and below center, that is, below average in the explanatory variable and below average in the response variable. And we'll see more in the upper right quadrant, where points that have above average values for both the explanatory and the response variable. So if you were to draw axes like the dashed red lines that go through the average x value and the average y value, you'll tend to see more points in the top right and lower left quadrants if the relationship is positive. When two variables share a linear relationship, we'll talk about the strength of that relationship. We'll say that the relationship is strong if the points on the scatter plot tend to be very tightly clustered around the line that defines the linear relationship. In this case, the explanatory value tells us a lot about the response. The relationship is very strong. A weak relationship is one in which the points on the scatter plot are not tightly clustered around the line. In this case, the y value has little to do, but still has something to do with the x value. For example, here are scatter plots for mother's height versus father's height, male's weight versus male's height, and mother's age versus father's age. How would we compare the strengths of these relationships? Which is strongest and which is weakest? The strongest is the one on the right. Notice how the points are all very tightly clustered around the green line that I've just drawn. The weakest is on the far left. There is still a relationship, but it's not terribly strong. Do you see how the points tend to be farther away from the line on the far left than they are on the right? The one in the middle is sort of a medium. We'll talk about how to put a number on this relationship in just a few minutes. Now let's look at an example where the direction is negative. Here's a scatter plot that displays price versus age for 14 used Pontiac Grand Ams, only the best for us. So on the vertical axis we have price, on the horizontal axis we have age. Why would we expect this relationship to be negative? And does this relationship appear to be linear And if so, is it weak or is it strong? We would expect this relationship to be negative because the older a car is, the less it tends to cost. So as age goes up, price goes down. This relationship does look linear, and it's a fairly strong one. If you notice, the oval that's drawn around the points is very narrow. Now, that notion of being a fairly strong relationship is pretty imprecise. So it's time for us to nail it down. Exactly how strong is a relationship when we say it's strong? What we're about to do is define the correlation, abbreviated R. The correlation talks about the direction and the strength of the linear relationship between two quantitative variables. There are two properties of R that we want to pay attention to. If R is positive, then the relationship is positive. In other words, the points on the scatter plot cluster around a line with positive slope, increasing from left to right. If R is negative, the relationship is negative. And if R is 0, there's absolutely no relationship between the two variables. The magnitude of R is also something we're interested in. Because of the way R is computed, we will always get a number between -1 and +1. If R is close to 1 or -1, in other words, it's close to 1 in absolute value, the relationship is strong. If R is actually equal to +1 or -1, then all of the points on the scatter plot fall on the same line. We would say all those points are collinear. So the closer R is to +1 or -1, the stronger the relationship is. If R is close to 0, then the relationship is weak. And if R is somewhere in the middle, we might say that the relationship is moderate. Let's consider some examples. Here we see the scatter plots that show relationships between price per kilogram versus price per pound for groceries, used car's age versus the year the car was made, and students' final exam score compared to at what point it was handed in. Now, one of these has correlation -1, one has correlation +1, the other has correlation 0. Which one is which? Well, if you look at the one on the left, all of those points lie on the same line. So, R is either +1 or -1. Since the slope is positive, R is +1. In the middle, all of these points lie on the same line, and the slope is negative, so R is -1. The graph on the right does not seem to exhibit much of a linear relationship at all. In fact, R is 0. The way that we interpret the fact that R equals 0 for the right-hand graph is, for that class, the order in which the exam was handed in has nothing to do with the final exam score. Let's go back to an example we've seen before. Here are the scatter plots for mother's height versus father's height, male's weight versus male's height, and mother's age versus father's age. Now, if I told you that these graphs have correlations 0.23, 0.78, and 0.65, can you tell me which is which? Earlier, we looked at the relative strengths of these and noticed that as we go from left to right, the correlation is stronger. Since all of these have positive correlations, then the correlations must appear in order from left to right as 0.23, 0.65, and 0.78. Because remember, the closer R is to 1, the stronger the relationship it's describing. Here's another example. For each of the 50 states, we're plotting the percent voting Republican on the y-axis versus the percent voting Democrat on the x-axis in the 2000 presidential election. The R value here is negative 0.96. That's close to -1, but not exactly -1. Why is it not perfect? Why is it negative? Well, it's negative because as the number voting Democrat goes up, the number voting Republican must necessarily go down. It's imperfect because there's a strong third-party candidate that year in Ralph Nader. Let's talk more about R. Remember that R tells the direction and the strength of the linear relationship between two quantitative variables. Remember that R only talks about the linear relationship. Two variables might have a curved relationship that's very strong, but R, which only measures linearity, would still be close to 0. We only use correlations when we're talking about two quantitative variables. If we're looking at categorical data, correlation is inappropriate. R is also unaffected by the roles of explanatory and response. R is unaffected by changes of units, and it overstates the strength of a relationship if it's based on averages. Let's look at these last three in order, starting with the first. R is unaffected by roles of explanatory and response. What does that mean? Well, what that means is if we have a scatter plot with, in the first one, weight versus height, weight on the y-axis, height on the x-axis, or if we switch the roles of the variables and we put height on the y-axis and weight on the x-axis, how do the directions and the strengths compare? Now, these scatter plots each show exactly the same set of data. But notice that they are both positive linear relationships, and they seem to be about equally strong. How do their correlations compare? Well, since they're both positive and they have about the same strength, we would expect the R to be the same for both, and it is. Now let's take a look at how R is unaffected by changing units. Here we see the plot for male students of weight versus height, where we measure weight in pounds and height in inches on the left, and then the same data set where we measure weight in kilograms and height in centimeters. Notice how the graphs still look pretty much exactly the same. So what's the comparison? The strengths are the same, the directions are the same, so R is the same in both cases. Finally, let's look at how R can overstate strength if it's based on averages. Here's a set of data for male students, height versus weight. But here, for each height that gets repeated, you can see, for example, for a height of 69 inches, there are 5 students. Here are their 5 weights: 125, 150, 172, 180, and 185. The mean of those 5 numbers is 162.4. So we could plot each of the data points, here they are on the left, or on the right, we can plot each of the heights along with the average weight in that category. One of these has an R of 0.87, the other has an R of 0.65. Which is which? Well, 0.87 is significantly stronger than 0.65, so the one on the right is the 0.87. Correlations based on averages are sometimes called ecological. We want to watch out for ecological correlations because they are artificially inflated. The reason why is that ecological correlations smooth out the individuality. It takes each of the individual points and collapses them down into one single point. So all that individual variation gets smoothed and ironed out. Now, we've been talking about how when we're looking at scatter plots, how we say they have a strong linear relationship if the points all tend to be clustered around some line. So here are some questions to ponder. When we say that the points cluster around a line, is there some line that's in some way better than all the other ones? If so, how can we find it? And if we find it, how might we use it? Well, if we can find it, we can use that line to make predictions. So if we know what the equation of the line is, if we have an x value with an unknown y value, we can plug that x value into the equation for the line to get a good guess at the y value. So if we write the equation of the line this way, y hat equals b sub 0 plus b sub 1 times x. Here, x is the explanatory variable. Y hat is the predicted response. B sub 0, or B naught, that's B in a UGHT. B naught is the y-intercept. B1 is the slope. So we plug in the value of our explanatory variable, and we get out, as y hat, the predicted value for the response variable. So if we know the line, we can use it to make predictions. So the question is, how do we find it? We want to find the line that makes the best predictions, since that's what we want to do with it. What does that mean? When we say we want to find the line that makes the best predictions, what we mean is we want to find the one that in some sense comes the closest as possible to all of the points in the scatter plot. The way we measure closeness is using least squares. We take the residuals, those are the prediction errors, so that's the distance of each point above or below our guess at what the line would be. Square all those residuals and find the line that makes the sum of those squares as small as possible. That's why we call the resulting line the least squares line. It's also called the regression line or the least squares regression line. The word regression in this case comes from Sir Francis Galton, who talked about regression to mediocrity, which we sometimes modernize as regression to the mean. You see that frequently in imperfect relationships, and we'll talk more about it later on. So if we define the best line as the one that minimizes errors, is there only one best line? Well, the answer is yes. And the reason why the answer is yes is because of some things that we learned from calculus. Many of you have never studied calculus, so you can just take my word for it. There is only one line. So what is that line? That best line has slope of r times the standard deviation of the y values divided by the standard deviation of the x values. And the y-intercept is the mean of the y's minus that slope we just computed times the mean of the x's. Some problems with this include the fact that we don't yet know how to find r. And these formulas are kind of messy. So let's take a moment to talk about how to use technology to find r and to find the equations of these lines. Let's start by looking at Excel. Here we see this scatter plot that we generated earlier using math and verbal SAT scores. To find the equation of the line,
that best fits the data, right-click on any one of the data points. One of the options that you'll see is Add Trend Line. Let's click on Add Trend Line, and we see the line magically appear on our data. If you think the relationship is something besides linear, you can choose that here in the Trend Line options. But if you look further down, you can see options for displaying the equation on the chart and displaying the R² value on the chart. Let's select both of those and go back to our chart. Let's make it good and big so that we can see, whoa, that went the wrong way, the equation of our line. There we see the equation of the line. It's 0.2826 times x plus 428.71, and we get an R² value of 0.0763. Why is it giving us R² instead of R? For some applications, R² is a better measure of the strength of the relationship. But we can use that to find R. To do so, just pick any cell and type equals SQRT for square root of, now let's type in our value for R², 0.0763. And we get an R value of 0.276225. Now, this will always be positive. We must always remember to go back and look at the linear relationship to see if it is positive or negative. Since it's positive, we'll leave this R alone. If it had been negative, we would change the sign to make it negative. Now, let's do the same thing using our calculators. We're using the same set of data, which hopefully is still entered into your calculator. Now, in order to find the equation of the regression line, we're going to go into our Stat menu, and I'm going to go over to Calc. And what I want is here in option 4, Linear Regression. We see a place to enter our X values and our Y values, and which lists we'll find them. We have already entered them into L1 and L2, so there's nothing we need to do. You can ignore frequency list. It may give you an option to store the regression equation. Don't worry about that. I'll show you how to find that in a moment. So let's push Enter, Enter, Enter. If you do want to store the regression equation, here's how you do it. Go to Variables, and then go over to Y Variables, select Function, and then pick, let's say, Y1. I'll push Enter one more time to get to Calculate, and I'll push Enter. And there is the equation of our regression. Notice that's the same thing we got with Excel a moment ago. However, I don't see R. So how do we find R? This is a little bit tricky, but you only have to do it once. Your R may already appear there, and if so, you can ignore these next few steps. If you don't see R here, we want to go into the function catalog. So I'll push second, and then catalog. And now I see a list of all of the functions that appear in our calculators. We want to go down, down, down. What we're looking for starts with the word diagnostic. So we're going to keep going until we find the word diagnostic. There we go. Diagnostic off, no, that's not what we want. We want diagnostic on. So I'm going to select diagnostic on and push enter and push enter again. It should say done. Now let's do the process for doing the regression one more time. Stat, calc, linear regression, L1, L2, no frequency list. We won't store the regression equation, and let's calculate. Now notice that we see the slope, the y-intercept, r squared, and r. This is everything we're going to need. If you wish to graph the line on top of your statistical scatter plot, just push graph if you stored the equation already. If you didn't, go to y equals, and let's pretend that the numbers weren't automatically there. So I'm going to, whoops, I typed, I hit clear and it's gone. So how can I get the regression equation back? Go back to variables. Notice there's an option for statistics. And you see EQ at the top. I'll go over until I get to EQ, that's equation. And the regression equation is here in option number 1. So if I choose option number 1, it's going to paste that equation right into Y1. Notice that plot 1 is highlighted up here. So it's going to try to graph the scatter plot as well as the equation of the line. And when I push graph, I get my line back. So that's how we use the calculator to perform regressions. Let's look at an example of using the regression line. Let's say we're looking at the Grand Ams again, and a car buyer wants to know if $4,000 is a fair price for an 8-year-old car. So if we look at 14 used cars and look at the scatter plot, which we've seen before, we can find the regression line, which you see here now. What you're seeing with these gray lines, like here and here, those vertical distances from the regression line are called the residuals. And remember, the least squares line wants to minimize the sum of the squares of those residuals. So let's say that we have found our regression line. The equation is price equals $14,686.30 minus $1,287.64 times the age. So for an 8-year-old car, we plug in 8 for the age. That will allow us to use the line to get the expected predicted price. So when we plug in 8, we get y hat equals $4,385. So $4,000 seems like a bargain. The star on the graph that has just appeared, that is our y hat. The red star, that's the actual y. So, to sum up, we looked at using a scatter plot to display a relationship between two quantitative variables. We talked about how to summarize the relationship using the form, the direction, and the strength. We talked about how R, the correlation, can tell us both the direction and the strength. We looked at several properties of the correlation, how it is unaffected by the roles of the explanatory and response variables, how it's unaffected by changing the units, and how it can overstate strength if it's based on average, that is, if it's an ecological correlation. We also talked about how we use the least squares regression line for predictions. I also showed you how to use your calculator and how to use Excel to find the equation of the regression line and to compute R.